Let us start. So good afternoon, everyone. Welcome to this edition of the NITheCS colloquium. My name is Francesco Petruccione. I'm the director of NITheCS, and this is a very special colloquium because it's intended as a public lecture organized together with the Department of Mathematics and Bosch University. And I would like to invite Professor Bruce Bartlett to introduce our speaker team. Yeah, so welcome to the two speakers. Bruce will make all the honors. Bruce, please.
Thanks so much, Professor Petruccione. This is Pi Week. On Friday, we have Pi Day. So we thought, as the mathematics department, let's team up with NITheCS and ask our esteemed speakers to come down and tell us this amazing story about Joseph Mokoena, South Africa's first Black PhD in mathematics. So our first speaker, Professor Loyiso Nongxa, he's retired ad hominem professor of mathematics at WITS. He is a previous VC at WITS. He was a Rhodes Scholar at Oxford, where he obtained his doctorate in mathematics. He has taught at the University of Lesotho, Natal, Western Cape, and WITS. He has served as the chair of the NRF. And since 2016, he has been a key advocate for the National Graduate Academy for Mathematical Sciences. And we're very thankful that you have come and speaking today. And our second speaker is Dr. Eder Kikianty, who was born in Berestagi, Indonesia, which is a rural area, I think. She comes from the farmland in Indonesia. She was telling us today that when she went to university, she had never seen a chemistry beaker in her life before. Anyway, she graduated with a PhD from Victoria University in Australia and worked briefly at the National ICT Australia before moving to South Africa. After postdocs at WITS and at UJ, she joined the University of Pretoria in 2016, and she's currently a senior lecturer at the WITS School of Mathematics. Her research interests include the geometry of Banach spaces, semi-inner product spaces, and the history of mathematics. So thank you, guys, for coming and giving us this talk. We really appreciate it. Over to you, Prof. Nongxa.
Good afternoon, everyone. I shaved a bit so that I don't look retired. I'm sure that you'd guess that I'm about 50 years old. Thank you very much to NITheCS and most importantly to Bruce. I think our interactions over the last week or two and your enthusiasm kind of has been really inspirational. We are going to be talking about a name that is hardly known in South Africa, even in mathematics circles. And this slide here gives little information about a prestigious award that he received from the South African government, namely Order Ifikamanga. But I'd like to bring your attention to this paragraph, which says that this was awarded for his exceptional contribution to the field of mathematics. And then the question is, what were his contributions? And secondly is that even in the bio that we came across, there's little that is written, in fact, about his mathematical contribution. It's only him as a revolutionary or as somebody who went into exile. So we felt that there's a need to do justice to what this wonderful man has done. And for me, it really is an inspirational story because of the context of the times that he lived in and the obstacles that he faced. Now I move that way. Okay. Now, what is exceptional to any of us? Now, that is a relative term. We start here with, why is this thing not? Okay. This is a picture of a Bebe Bigila. He is pictured winning the marathon in the Olympics in 1960. He won that in record time, but he was not wearing shoes. And his record of running a marathon without shoes still stands today. So if you want to break his record, you can enter one of the marathons and try and break it. That is remarkable. But look at the time that he took to finish that. It's 2 hours, 16 minutes, right? Now, the record for women is, in fact, yeah, this is 2 hours, 9 minutes, right? And now you can compare a male whose record is 2 hours, 16 minutes to a female who ran it in less than 2 hours, 10 minutes. And that was the record for men until maybe about 10 years ago. Which of those two is an exceptional achievement? Oops, sorry. I'm struggling. I think I've skipped a few slides. Look, can I, sorry, I'm not able to use that. I want to move it that way. This is part of a project that Eder and I spoke about in terms of history of South African mathematical research. One of the things that we came across was a book that was written to celebrate the centenary of the South African Royal Society. Different chapters written on different disciplines about how they evolved in South Africa. And there's no word about how mathematics has evolved in South Africa. Later on in 2011, the physics people went further and just concentrated on how physics has evolved in South Africa since maybe the colonial days. You can find a history of the South African Mathematical Society on the South African Mathematical Sciences website. But by and large, there is very little that we can find about how mathematical ideas took root and evolved in South Africa over the years, and what research themes have been covered, and who were the influential people in introducing those areas of study. So the question is, this big project that initially were ambitious that we could embark on, what are the topics that could possibly be addressed in writing about the history of mathematical sciences research? Things that you come across in other science systems would be women in mathematics, and we can talk here about South African women in mathematics. And by the way, the first PhD that was awarded to a female mathematician in South Africa was awarded by Stellenbosch University as recent as 1971. And that is Henda Swart, who is regarded as the mother of graph theory in South Africa. The number of people working in category theory, but up to maybe the early 60s, there was nobody doing research in category theory. The question could be asked, who introduced category theory in South Africa? Or who are the people who were the first to achieve certain things? Evolution of graph theory, it's a topic that we have written about, and I gave a presentation to a conference of graph theorists, being scared that they would tell me that I know nothing about graph theory, which is true. Another topic would be how mathematics research evolved in various mathematics departments in South Africa. And I believe that this has been written about here in Stellenbosch by Professor Maritz. Yeah, we have tried to get a copy of that, not here, okay? And who supervised who in terms of the people that have finished PhD in South Africa. And our belief is that no self-respecting community in mathematical sciences should not be able to answer certain basic questions like the one we have listed here about how mathematics has evolved. Now, it's generally accepted that the lecture that was given by David Hilbert at the International Congress of Mathematicians in Paris, and that was 1900, shaped the development of mathematics research during the first half of the 20th century. And in fact, some of the questions that he posed amongst the 23 questions still have not been solved. Something like, I think, the Riemann hypothesis, the Goldbach conjecture, which states that any any integer, positive integer is the sum of two prime numbers. Now, I'm not going to read this to demonstrate that I can read English, but essentially, the thrust of what he is saying here is that a discipline remains vibrant when people are engaged with questions that advance that discipline. He's not saying that the research in mathematics is only about publishing in journals. It's that we tackle questions that would in fact open vistas of knowledge and investigation in other areas of mathematics. Now, other systems have done this, looking at how people who have been marginalized in their societies have, despite the odds, managed to contribute to the advancement of mathematics. I think some of you would have seen, because it's a movie house, the film of Hidden Figures about space travel. And it's about 3 African American women who were really instrumental in doing the background work in terms of the calculations that informs that project. On the left-hand side, I became aware of this. Apparently, it's more than so many months. This movie here, Journeys of Black Mathematicians, Forging Resilience. And there's a book that kind of informed our study, Beyond Banneker, Black Mathematicians and the Path to Excellence. All these are mathematicians in the United States of America. Okay? Now, when we looked at the records, we always believed that Ismail Muhammad was the first Black South African to get a PhD, and he finished his PhD in 1960 from Queen Mary College at the University of London. It's only in 2022, when WITS was celebrating its centenary, and a friend of mine, Yunus Balim, I would like to thank him for that. If he's listening, I'm sure he's not. We were chatting, and he had been asked to review the second edition of a book by Bruce Murray. And he drew our attention to this section here in the book that J.A. Mokoena finished his PhD at WITS. But what I want to highlight here is that this information is really about James Hyslop. Okay? This paragraph is not talking about Mokoena. It's talking about James Hyslop. So a reference to Joe Mokoena is in relation to that he was a student of Hyslop. And he's not mentioned in his own right by WITS as somebody who was the first PhD in mathematics awarded by WITS University. That is also instructive. All right. There's some sources that we found on the South African government. I've already indicated that he was awarded posthumously the Order of Ikamanga in gold. Besides his PhD thesis that Eder is going to show you and talk about, we found only one publication that he wrote. And you could say that, why are we wasting your time talking about somebody with only one publication when maybe many people in the room here who are early career academics have more than 20 publications? Joseph Mokoena was born in a township called Everton, which is just outside Vereeniging. So one believes that just looking at his background, somebody who was born, let's say, in an environment like Guguletu or Kayamandi or Mdantsane or Soweto, right? Went all the way to finish a PhD in mathematics. And I'll tell you why that is remarkable. Many of us, of course, know about O.R. Tambo. There's even a an airport, I said passport. There's an airport named after him. Something that, again, many South Africans are not aware of is that Oliver Tambo majored in mathematics and physics. But in what we read about him, it's that he practiced law with Nelson Mandela, and that, in fact, he was the leader of the ANC for many years in exile. It came as a surprise to some of us that he majored in mathematics and science and was a science teacher before he went into exile. There are some quotes. There's a biography of O.R. Tambo written by Kalikonis. Yeah. And these are quotes for them that Oliver Tambo is saying that Oliver Tambo is really revered by people in the liberation organization who were in exile, that he was a smart man. And basically here he says that Joseph Mokoena was smarter than him. Their achievements were that They were amongst the first two, the two Africans who passed the junior certificate with a first-class degree. And what we have not mentioned here is that during that year, they were in the top 3 in terms of their performance in an exam that was written by students from all different backgrounds of all races. And I must emphasize that this was during the dark days of apartheid, when there were separate government departments for education for different races. Now, this is a picture that comes from the biography of Oliver Tambo. I'm going to talk about a little bit about Joseph's son. I sent him this picture and said that, okay, your father is here. Which one is he? And he said, he's the one to the left. And I was a bit confused whether it's to the left as I'm standing here of the picture, or is the left when you're facing that. And we had this to and fro by WhatsApp. He said, Professor, don't you distinguish between your left-hand side and the right-hand side? So Joseph is, so he's the first one who's sitting in the middle row on that side. That is him. And another picture here, he is on the extreme left, and the person who's sitting in the middle is Oliver Tambo. Again, this is a story about Oliver Tambo, and Mokoena maybe is just seen as one of the people who were around Oliver Tambo. Now, Professor Kikianty and I are not historians. We are mathematicians. And there's a methodology in doing research in certain areas, okay? And there are quite a number of challenges that we've faced in actually coming up with something much more kind of solid than we have. First of all, that Joseph Mokoena attended St. Peter's School, which was a fairly prestigious school at the time. And when we reached out to the Department of Education in Gauteng, or people who know about that, they said that that school no longer exists. And its records and everything have been transferred to, I think, St. Patrick's. Okay? We reached out to St. Patrick's and we're told that, unfortunately, the records of St. Peter's were destroyed by fire. This is a common trend when one tries to find out background information, especially about what happened colonial days and so on, especially when it comes to the Black communities, which makes it difficult then to tell the stories of the people who lived that time. Joseph Mokoena attended Fort Hare University and later taught there for about 10 years. Fort Hare celebrated its centenary in 2016. And we felt that, they were writing the history of Fort Hare. And we reached out to find out if we could find any information about Joseph Mokoena, who was the head of department, what courses did he teach, what was his record when he was a student there. Nothing in Fort Hare records about Joseph Mokoena. And the one that personally I found really frustrating was that I was given the contact of his one of his sons who lives in Botswana. He's a retired academic. I called him and he was quite upset that I had interrupted his shopping. He was at a shopping mall. And then I said, okay, how can I reach you? So he sounds surprised. He said, Professor, these days are things called email. You can use that. Anyway, so we sent him a list of questions, something about basic things like about his parents. Mother is from Port Elizabeth, Xhosa speaking. Father, of course, I think would be Sotho or Tswana. Right? Nothing. And about his own siblings, what happened to them? Nothing. Then he started sending me YouTube videos about politicians. I would wake up in the middle of the night and find this YouTube about politicians. Now, honestly, we have not found any kind of information from him, photographs of his family, etc., nothing like that. Again, the difficulty that we face in telling the full story about this wonderful man. Question is, does this matter? Does the story of Joseph Mokoena or Henda Swart or Hanno Rund, who was the first PhD in mathematics in 1951, awarded by South Africa, UCT College, do those stories matter? First of all is that in mathematics research, there is a category of the history of mathematics with many different categories. One is on ethnomathematics, which was quite popular in South Africa in the 90s, 80s. Questions is how did mathematics, as I've already raised this, how did mathematics evolve in South Africa? Why are there certain areas of mathematics, specialities, that are not covered in South Africa? Can ask questions about who was the first female to earn a PhD or a black person, etc., etc. Now, I find the story of Joseph Mokoena quite inspirational because he went to Fort Hare, finished his honors. He did his master's by correspondence at UNISA. I think even his honors by correspondence at UNISA, which therefore means that he had to study on his own. He did his master's at UNISA as well, of course. We haven't found information about his supervisor. And something remarkable about his PhD, he started corresponding, Eder will talk about that, with a Harvard professor when he applied for a scholarship and went to Brown University, which led to his PhD. And from the early 50s until he finished his PhD in 58, he was corresponding with this professor. And dare I say, during that time, there was no email that this guy reminded me about. So he had to write letters and wait for maybe 2 months or 3 months before you get a response. And that persistence over a period of 7 or 8 years is something that should inspire those people who feel that, well, they don't receive help from their lecturers, their supervisors, and so on. Sometimes I think, in conclusion, I'm going to hand over to Eder, is that I went to Fort Hare myself and did my first degree, honors, and masters. And during that time, which was, now I'm going to reveal my age, this was in the 70s when I was studying at Fort Hare. There was only one lecturer who had a PhD in mathematics. This is 14 years after Mokoena finished his PhD. And one of the questions that I kind of mull over is whether he would have been promoted to the level of a professor to be ahead over our white lecturers, who really sometimes showed us they did not have confidence that would understand mathematics. Professor of mathematics that taught me analysis in 3rd year, whenever you raise up your hand and say, Professor, I don't understand that. And he said that, ooh, we will understand that next year, which meant that you'll be in the same class next year repeating analysis. I'm going to hand over now to Eder to talk about the mathematics of Joseph Mokoena. Thank you.
Thank you. Thank you, Loyiso. First of all, of course, I want to thank Professor Petruccioni and this invitation from NITheCS as well as the mathematics department, especially to Bruce, who was organizing all of this. And Bruce, myself, and Naina have been discussing about the thesis. I have it here in my hand. I remember when Loyiso gave it the first time to me, we said, let's go check out his PhD thesis in the WITS archive. At the time, I was still working in Pretoria, and then Loyiso went to the library and he gave it to me. I still remember he came past my apartment. We were outside, he gave it to me, and I said to Loyiso, we're holding history right in our hands. And yeah, it's been a journey since then. So I have it here, nicely, freshly bound by the librarian of WITS. This is what they told me, because the old copy, the old cover was falling apart. So it's good that they rebound it. Anyway, so I have here, as you can see, a little bit of an excerpt from the front page of the thesis. So Loyiso already mentioned that Dr. Mokoena went at some point to Brown, and we didn't know what the circumstance, what was the scholarship about, because we could not find any record. But point is that when he was there, he saw papers by David Vernon Vidder, who's talking about integral transforms. Okay, and he mentioned here, so that's the original copy. I just make another excerpt here just for you to see, and I'm not going to read everything, but I'd like to point out what Loyiso said earlier. through correspondence with Professor Eder, who generously gave me free copies of his papers. Obviously, back then, it's not like we can go on Google and just say, I want this paper and download it. It's very difficult back then. And it's this persistence and, the even confidence to write to somebody at Harvard and say, hi, I'm interested in your work. Can I get a copy of your paper? And also we have to thank Eder as well to, be so generous with an aspiring mathematician at the time to, share his work. Okay. So then Mokoena became interested in studying integral transforms based on Eder's work. If you look at, this is the front page of his thesis. The title says, "An inversion of general class of Lambert-type integral transform." And he, obviously generalized. Lambert integral is basically what Eder's working. I will mention a little bit later. He generalized the work, and then the work by Eder become a special case. That's essentially the idea. But I would like you to please look at that phrase, Lambert-type integral transform. If you remember anything out of this talk, maybe it's these 4 words, Lambert-type integral transform, because it's going to come back in a little bit. Okay, so you might be thinking, as Loyiso said earlier, this person only has 1 publication and a doctoral dissertation. Why should we care about his work? Okay, this might be a little bit of a detour, but let me take you on the detour first, and then you'll see why. Okay, so if some of you here seen this before, I think you have an idea of what I'm going to talk about. But if you don't worry about it. I'm gonna bring you to it. Okay, so what I'm going to talk about is one of the unsolved problems in mathematics, which is the Riemann hypothesis. And what is it? It started with the Riemann zeta function. So the Riemann zeta function is defined as follows. If you have S, which is a number greater than 1, and you look at this series, 1 over n to the power s. So it's basically the series of 1 over 1 to the s, plus 1 over 2 to the s, and so on and so forth. You ask the question, does this converge? The answer is yes, when s is greater than 1. And where does it converge? Of course, one of the most famous cases is when s is equal to 2. This is Basel's problem. The sum of the reciprocal of square is pi squared over 6. So it converges to that number. And in honor of Pi Day, I'm glad that we have some pi in our slide today. So, yeah, and it's surprising why pi show up. If you're interested, there's very nice videos on YouTube. I'm a big fan of 3 Blue 1 Brown. If you haven't seen his videos on Riemann hypothesis, you should, because it's amazing. Okay, then the question came when Riemann started working on these things. He said, can we extend this to a larger domain, right? Instead of just s greater than 1. And he started looking at the domain being complex numbers. And the idea is just if your real part is greater than 1, it's what you saw earlier. But what about everywhere else? So I'm just gonna say, I copied this from 3 Blue 1 Brown. It's something, okay? Because it's gonna be another 2-hour lecture or perhaps more if we started talking about this. But the key phrase you want, if you're interested more about it, is analytic continuation. Okay. Of course, if you know about this, the one funny thing about analytic continuation is that if you look at the analytic continuation of Riemann zeta function at -1, you get -1 over 12. And if you just, for fun, even though you're not supposed to do this, you plug in s equals -1 into that series, what do you get? 1 over 1 to the -1, which is 1, plus 1 over 2 to the -1, which is 2. So you're adding all the natural numbers, and you get -1 over 12, which is silly, right? So you're not supposed to think about it like that, but it's often misinterpreted as the sum of all natural numbers is -1 over 12. Anyway. So if you want $1 million, you should answer this question. When is for what s is zeta function equal to 0? And I took this from the Clay Mathematics Institute website, talking about Riemann hypothesis. If you work with closely with the Riemann zeta function, there's something called the trivial zeros. I like what 3 Blue 1 Brown said in his video, is that mathematicians like to say trivial, even though it's actually not that obvious. So on the negative numbers, there's your trivial zeros. And the remaining question is, there are non-trivial zeros, but we don't know exactly where they are. All you know, it is somewhere in the critical strip So real line equals 0 is a line basically going vertically on your complex plane, and real equals 1 is also a line. So you have this little strip, of course, not including the boundaries, and the non-trivial 0 sits somewhere there. That's the only thing we know. And then Riemann hypothesized that, before that, I forgot about this little note. The position of these zeros actually encodes some information on the prime numbers, the distribution of prime numbers. Of course, prime numbers, as we know, doesn't follow nice patterns. So every time somebody talk about prime numbers, you want to see some patterns, right? Okay, so now here it is. Riemann hypothesis. The hypothesis by Riemann is that the non-trivial zeros actually lie exactly in the middle of that strip. So when the real part is equal to half. Of course, this is not solved. So as I said, if you want $1 million, maybe this is something that you can work towards. Okay, so that's Riemann hypothesis. So there are many attempts to work towards proving Riemann hypothesis. I saw this book online by Kevin Brown, Equivalence of the Riemann hypothesis. So the whole book talking about equivalent statement to Riemann hypothesis. Often in mathematics, when you can't prove something, you try to prove something equivalent to it. So I thought, wow, an entire book just for equivalent of the Riemann hypothesis. How wonderful! And then, when you're on the internet, you started clicking, and then I saw, oh, there's volume 2. So volume 1 is arithmetic equivalence. Volume 2 is analytic equivalence. And then I thought, wow, this is wonderful, 2 books, but it doesn't stop there. There's a 3rd book. Further steps towards resolving the Riemann hypothesis. So I thought, okay, people working a lot on this. I didn't know that much because it's generally not my area, to be honest, but I'm getting super interested in this whole thing. Anyway, and this is credit to Naina and Bruce. We've been talking over WhatsApp the last few weeks, and Naina and Bruce told me about this paper here. If you look at the title, very catchy, Approaching the Riemann Hypothesis, using Salem's equivalence. So we looked up who Salem was. He's established a connection between the Riemann hypothesis and equivalence via an integral equation in 1953. Okay, and then if you look at this paper, it's very recent. I don't know if you can see it from there, but it's 2024. So it was published last year. And of course, I mentioned to you earlier, if anything you want to remember today is the word Lambert-type transform. Okay, so, and also Witter's name is mentioned there, Witter-Lambert-type transform. So now there's a connection, right? There's a connection between the Riemann hypothesis and Lambert-type transform, Lambert transform. Then I started scrolling through this paper. I didn't study it in details, but I saw that there's a generalization of Lambert transform in it by somebody named Richard Robinson Goldberg. Who is this person? Goldberg was the PhD student of Witter, okay? And in fact, we studied the paper. I looked at the paper by Goldberg, and the generalization is eerily similar to what we saw in this dissertation. And it's our belief that they actually work separately. They never work together. And there's actually differences between the two. It looks similar, but there are differences which I will guide you through there as well. But the point is, of course, there's no mention of Mokoena anywhere in this paper, which is, we know why, because his work is not known to the community, not to South Africans, not to the mathematical community, especially people who work in integral transform area. And this is one thing that Bruce tried to push me, is to contact the librarian at WITS to make this available digitally so that we can share this with the mathematical community. So this is what I'm trying to push right now. I'm in conversations with the WITS librarian in order to do this. Okay, so let's see a little bit. I hope I can mention why integral transform is important and point out the highlights for you. Okay, so the Laplace transform is one of the integral transform that is well known in mathematics. So I always view that mathematics like to do something like this. There's a difficult problem, right? You translate it to something easier, you work there, and then you transfer back. So there's this transformation going here, and there's an inverse going back. So this is why people care about integral transform, because sometimes it's very difficult in this space, but you can move towards another space, solve it there, and then go back, right? So it's important to know how to get there and how to go back, right? So the Laplace transform, you can see it as a continuous analog of that power series that is given up there for some discrete function an and x to the n. And if you just squint and change that sum into an integral, right, your discrete function a becomes a function f, your discrete variable n becomes t, right, and you replace your x with e to the minus x, and again that n has become t, then you get your Laplace transform. And then what Eder did is that, okay, let's change that series. And he looked at a series by Lambert, hence the name Lambert transform. This is my series. Let me look at an associated transform. So you see there, the function changed to that function, the x changed to the e minus x, the n changes to t, some algebra, and voila, you get this form over here. Okay, I'm gonna move to the next slide, but you will see in the next slide that the integral transform should be there still. Okay, so in fact, if you consider something quite specific, your x is equal to 1, and your f of t is equal to t to the 1 minus s. And I believe some people who are working in number theory are probably very familiar with what is happening up there. This is the identity that Eder is using, that integral is equal to gamma function multiplied with the zeta function. Okay, and the zeta function, as we saw earlier, has the following representation. And the kernel of that transformation has the following representation. And then comes Mokoena. He saw this relationship between that integral, gamma function over there, looks like that one, but now there's something else in there instead of the zeta function, and it is this series Ls, right, given as follows. And then he looked at the kernel of that guy, can be represented like this, and then again, if you squint, right, there's very similarities here, right, the s and the t and the n with e to the n, and similarly here. Minus 1 to n minus 1, and here you have s becomes t, and that has been replaced with e to the n to n minus 1. Okay, so he said this is nice. This relationship is nice. He said, oh, maybe I can go further. Then he realized, okay, I'm just gonna make this guy here replaced by a general series which he called E, satisfying certain properties. So the properties he mentioned was A1 is 1, AN is bounded, and it satisfied the following condition, that A of m times n is A times m multiplied with A times n, sorry, A of m multiplied with A of n, where m and n are co-prime integers. Yeah, their greatest common divisor is 1. Okay. So then Mokoena looked at this. Yeah, this is a generalization of that guy and that guy. If you make an to be 1 everywhere, you get the zeta function. If you get a is given by this lambda, where lambda n for n odd is given by minus 1 to the n minus 1 over 2 and 0 otherwise, then E becomes this L. And I don't know if I can't see where Nina is, but this is a Dirichlet character of order 4. Is that right? Yes. So thank you, Nina. You know more number theory than me, obviously. I know very little. So thank you for your help. Okay. So this is where he's at. Okay. And then with that, I have this little table for you. What's the series? What's the kernel? What's the integral transform? That's the version by Eder. Zeta function, that's your kernel, that's your transform. Mokoena's first generalization with the L, that's your kernel, that's your transform. And this is his generalized version. That's your series, that's your kernel, and the generalized version look like this. Okay. So if you don't remember how it looks like, and if we need it, I'm gonna show it on the screen when necessary. Okay, but this is the most general version, right? In which that one and that one becomes special case. Okay. Important remark. As I said earlier, we need to transform something and then get back to the original problem, so you need to find the inverse. I thought I should not show the inverse formula because it is longer than the slide, A. And then B, I thought that's not the point of the story. So I'm just gonna tell you the idea by Mokoena where this is gonna become important. Okay, so he tried to find the inverse formula for the integral transform, and he started with that series, ES, and tried to look at its reciprocal. Okay, and recall ES looks like this, and that second condition are commonly known as multiplicative function. Then a snapshot from the thesis of Mokoena said that under the conditions imposed on A, which is these guys, the functions ES admits the following infinite product representation, which is this one here. Okay, and again, thank you for Naina and Bruce for pointing this out, that this infinite representation actually works only for completely multiplicative function. What does it mean? This has to be changed to any positive integer m and n. Okay, so there's a slight mistake there, but the two examples that you saw earlier actually are completely multiplicative functions. Okay, so let me summarize for you. This is our correction that now becomes completely multiplicative, and you can show that for the first case when an is 1 for all n, this is a completely multiplicative function, and the lambda is also a completely multiplicative function. So all his examples work with just that slight tweak, which is not too bad, I think, of a tweak. Okay, so there's an important correction over there. But furthermore, the 1 over e to the s also has this property, right? Also has this representation of some sum multiplied with 1 over n to the s with some discrete function b. And this discrete function b has the following properties. B1 is 1. Bn is minus 1 to the r multiplied with a of n, when n is the product of r distinct prime and 0 otherwise. And the number theorists might see this is familiar because when e is zeta, b is none other than the Mobius function. Of course, when you just plug in a equals 1, you get the Mobius function over here, and we have this relationship right here. So the idea of the generalization by Mokoena to find the inverse is to utilize that in this case, the Mobius function has a close relationship with the zeta function, and you try to generalize that. Okay. Now, if you multiply these guys, you end up with the following property, that a1 b1 is equal to 1, and the sum of AP with b over n over p is 0 when n is greater than 1, and this sum runs through all the divisors of n. Okay, I put it there because there's a reason for it when I talk about Goldberg. All right, so Goldberg's generalization, also in 1958. He wrote a paper based on his thesis, published in 1958, and he basically just mentioned that he's generalizing the work of his supervisor for a general class of non-negative sequences, AK. So if you look at this, I think I'm going to bring Mokoena's back over there just for comparison. There's FT there. FT looks similar. AK. Okay, he write the discrete function as a sequence, which is basically the same thing. And e to the k, e to the minus kxt. The k here is n here, similar thing, right? So this and this actually look very similar, right? In fact, looks the same. But of course, maybe there's differences between these a's, right? And then if you dig a little deeper, you will see, oh, before that, let me just mention that Goldberg also, of course, talked about the inverse because that's important. And the way he obtained the inverse is try to generalize this property for an appropriate B that is given. Let me put it like this. Let me rehash. He chose a class A, and then he looked at this property, and he find B that satisfies those. That's his idea. So a little bit different idea, but it ended up going to the same direction, basically, with Mokoena. But if you recall here, right, that it should come now. There you go. Goldberg wanted something non-negative. Obviously, if you look at that lambda, this can be negative, right? So this is not an instance of Goldberg's AK, but that's actually where Mokoena started with. So they have the same form, but they're not exactly the same generalization. So I believe this needs to be looked at, right? So to sum up, I mentioned that there are similarities between Mokoena's generalization and Goldberg's generalization, but there are some differences in defining these A's. So if we're going to approach Riemann hypothesis with Lambert-type transform, I think it's also fair to look at what Mokoena did. And this should be recognized by the mathematical community, by the people working in this paper, maybe we'll reach out to these authors. I don't know. But the idea is that the work is not known for a lot of reasons. And even us, we didn't know about his name until a few years ago. But thanks to all the digging and the support from people, this project is the first step to make his work known. And we're going to try and, as I said, digitize, reach out to people, make it public, talking to people, informing everyone. So again, I would like to thank NITheCS and Bruce and everybody for inviting us down here, because I believe this is also part of the first steps in preaching about Mokoena's work. And with that, I'll end here. Thank you very much.
Thank you very much to both speakers for a very motivational and inspiring talk. I'm sure we have plenty of questions in the, here we go. Here comes question number one. The microphone is coming from the back. Because we need to share one here, so we keep it close.
Thanks for a great talk, both talks. You mentioned that the paper he published was solving a differential equation. Can you tell us a little bit about that?
I actually just got to be honest that I did not look through it in details, but there's a copy available online. If you go to Google Scholar, you can find it. It's a very short paper, like 3 pages, 2 pages. Yeah, yeah, it's very short. Yeah.
Thank you very much. Such a beautiful talk and very inspiring story as well. So this issue that you pointed out about multiplicate property, what about the other PhD student? How did he deal with that? Did he have a correct version, or did he?
I think it's different generalization, because he doesn't consider similar classes of A.
Right.
Yeah.
Okay. So that thing doesn't come
That
up.
thing doesn't really play the same role. He kind of worked backwards. You have that series, and then he's find the B that satisfy that with a given A.
Is it somehow possible that whatever is in common to the two of them was an idea that maybe was suggested by the supervisor, and they took this idea in different directions? Is there any evidence of that in the introduction of the thesis? Have you looked at the thesis of the other student?
We have not, but I...
No, I mean, became aware of the paper itself, and we haven't come across any evidence that they were in correspondence, namely Bullbeck and Mokoena.
No, but what I mean is that maybe the supervisor had some kind of initial idea that he gave to both of them. It will be interesting to know if maybe there is something that he gave to both students, and then the students took them in slightly different directions.
Yeah. I think one can only speculate at this point, but hard to say. Yeah.
Thank you. Thank you.
Yeah, thank you so much for a very inspiring talk. I'm just curious what started you on this journey? Like what led to you becoming interested in this mathematician?
I'm gonna hand over to Loyiso.
No, I tried to describe it in the first 3 slides. Maybe I can relate a story that when about 10, 15 years ago, we were lobbying for the establishment of the Center of Excellence, which is hosted by WITS. Whenever I went to universities overseas, because there was a requirement that we should set up partnerships with universities elsewhere, people would ask me, what can you tell us about South African mathematics? And then, of course, I'll say, oh, yeah, we have people who are rated A, B, C. But outside of South Africa, there's no knowledge of rating. So people expect us to say, oh, yeah, the work that we're proud of is numerical analysis or category theory. We have Professor Janelidze, who has done something on Galois theory in categories, et cetera, et cetera. So not being able to tell people about mathematics or physics or biology in your own country, but maybe you can say that, well, Nobel Prize winner in molecular biology, Watson and Crick in Cambridge and so on. So it's really to fill that gap. It's a real gap about how ideas, scientific ideas, in this case in mathematics, have evolved in South Africa and who were the influential voices. Eder?
Yeah. Yeah, what before that, I can add a little bit as well that when Loyiso was made aware of, I think Jacek was the one who introduced the two of us in the end. At the time, there was a historian of mathematics visiting Pretoria, so her and I started talking and started this journey. But then Loyiso and I sort of we said we want to focus more on the mathematical research side of South Africa. Yeah.
There is something else that I just want to mention this point. There's an area of mathematics called, I tease people about this, is point-free topology. And we call it pointless topology. What is the point of pointless topology? The person whose work, in fact, laid the foundation for point-free topology is Donna Strauss, who's South African. And I think that she's the first female in South Africa who did a PhD, but her PhD is from Cambridge. Yeah. And she also was a political activist against the Vietnam War.
With regard to the earlier question of what instructions Eder might have, or guidance he might have given each of these students, is there any record of the letters, either from his side or from either of the student side? So there's no remaining record at Brown or Harvard or anything of these letters?
We have not come across any of this, Nancy, and we would like to, because we're really, so interested in these kind of stories, but difficult. It's difficult to find these. We were hoping very much when you make contact with the son. Yeah. And I was so happy. I said, Loyiso, finally we're gonna get some answers. And unfortunately, we interrupted his shopping, and that's that.
Of course. Just out of curiosity, his PhD was 1958. How does that compare with similar first PhDs in other African countries? Do you know of anyone that did a PhD before or soon afterwards?
I've looked at that. There's a university, I think University of New York in Buffalo. Is Buffalo in New York State? There is I think there's information about Black PhDs from Africa. Yeah. But I can't recall whether there are people who obtained their PhDs earlier. Maybe. Okay. There's a hand up there. Okay.
Oh. Online.
Oh, that's Arun.
Hi, Loyiso, can you hear me?
Arun, you're welcome to ask your question. You should have the right to speak in Zoom.
Hi, can you hear me? Hello? Hello, can you hear me? Okay. Loyiso, why did Mokoena only publish one paper?
Do you have questions from the audience?
We have a number of comments and one question. Okay, so just some comments first. Rebecca Waldecker says, 2 great talks, thank you. Sean Bozolek says, thank you, fantastic history, inspiring. Mulalo says, great talks, very refreshing to have a different view to see mathematics in South Africa. And then we have a question here from Barry Green. Thank you for a very interesting talk. Do you know if there's anything about the distribution of primes, say, following Goldberg's work?
She knows the mathematics.
I should say I don't know. I don't know this very well. This work. That paper was. I think I saw this paper about a week ago and didn't really have time to go through properly. But if Barry would like to, I can send an article or a link to it.
I just want to make a comment. I think, Loyiso, you proposed not only with the talk, but also with the specific comment that you made at the end, and a very, very good idea of speaking actually about mathematics of South African mathematicians, rather than publication numbers and these kinds of things. And this was such an excellent talk, giving an example. And maybe we really need more of that, and also for mathematicians who are alive, not just the ones who are in our past of history, but also those who are active currently. Maybe it's a good tradition to have talks about mathematicians, and not necessarily your own work, but somebody else's work. This is fantastic, fantastic idea and fantastic talk. Thank you.
There are no more questions. Then let's thank very much our two speakers. Thank you very much.